my pleasure to introduce our first speaker, Yang Yu.
So hello everyone. I'm gonna give a presentation of our work about partially observable Monte-Carlo graph search. So my name is Yang Yu. I'm currently work at UKEA, and I'm now also a postdoc at Oxford Robotics Institute. And before I went to UK, I graduated my PhD in Iran, Nancy, in France. So I saw a lot of French friends here. Okay, so POMDPs. I think everyone loves POMDPs, right? POMDP is a really powerful mathematical tool that models a single agent's decision-making problem with uncertainties. And formally, a POMDP is defined by state, actions, observations, dynamics, reward function, and usually with a discount factor. And since POMDP agent usually not directly observe the true state, so at each time step, the agent needs to maintain a probability distribution over the true state. Usually we call this belief. And the goal of solving a POMDP is to find a policy that is a mapping from belief to actions to maximize the discounted expected return. And in this presentation, we will mainly focus on the planning method. So there are also learning methods, but today we are mainly focusing on planning. So currently, there are two categories. Usually, you have offline planning, where you're trying to solve the problem and derive a complete policy, such as a classic algorithm like HSVI sucks up. We have Hannah here. And we also have online planning methods. So in this case, you just try to find the best action for a given belief. You have typical algorithm like POMCB or Despot. And we first look at offline POMDP planning. So for offline POMDP planning, you are really trying to solve the true optimal value function. And this is the maximum Q values. So you are trying to find the best instant reward plus the discounted future return. And currently, almost all offline methods are point-based methods. So such as HSVI sucks up, they are performing value iterations on reachable belief points. So usually we call this value iteration Bellman backups. And we can view this as a bottom-up dynamic programming way, because if you want to solve the optimal value function given B, you also need to compute the optimal value function given the next belief when you execute an action A and receive opposition O. So it's like a bottom-up approach. However, for large problems, usually you need to have like hundreds or thousands of Bellman backups, and the computational costs increase rapidly with problem size and horizons. So what about online POMDP planning? So currently, typical online POMDP planning methods are usually all tree search-based approach, especially with typical method like POMCP. So in a POMCP, you start with a belief, you sample one state particle from the belief, and you do Monte-Carlo simulations. And for each encountered action observation history, you create a new policy tree node. And for example, for the new added policy tree node, you perform a rollout evaluation, and this rollout policy could be a random policy or could be something else you provided. And then you back propagate the value until the root. So the idea is that with more Monte-Carlo simulations, the nodes closer to the root become more accurate, and in the end, you just execute the best action stored in the root, and then you start the next planning phase. But why usually people use this tree search approach to do online planning? Because it's quite fast. And why it's fast? Because usually online planning just have a lightweight forward simulations. You only simulate trajectories from the current belief. And you can view this as like a top-down refinement, so quite different from the offline method. So you are gradually improve the policy in a top-down manner. So like I said, the nodes closer to the roots is more accurate, and the nodes closer to the leaf are less accurate. Okay, so currently, at least in the last decade, most state-of-the-art POMDP planning methods are online methods because it scales, and But still, there are some applications require you to have a complete policy. For example, if you have a robot deployment task, for example, sending the robot to a nuclear power plant, you really want the robot can safely get out. And to do that, you want to validate your policy before you're embedding it, before you execute those policies. And you want to make sure the robot don't do something stupid. And there are some safety critical requirements required to have a complete policy. However, for large POM-DPs, usually offline methods cannot or struggle to scale. And this forms our main motivation. So can we draw inspirations from online methods to design a new offline POM-DP planner? So it can be fast and it can scale. So what about we just try to naively give sufficient planning time for online planning methods and let the policy tree get fully expanded? Can this work? Well, practically not, because the policy tree size grows exponentially with horizons. For example, even with a very small problem like tiger problem, you have 3 actions, you have 2 observations. If you give like a horizon 40, then eventually if the policy tree gets fully expanded, you will have this number of policy tree nodes. So it's memory infeasible to store such large number of nodes in large POM-DPs. So you cannot just naively use the previous online methods to derive an offline policy. And here comes our contribution. So we propose a partially observable Monte-Carlo graph search method. So the key innovation is that we merge similar belief nodes to form a compact policy graph, or also known as finite state controller. And we can construct a finite state controller, or FSC, through Monte Carlo simulations on the fly. And this results to a fast and sampling-based offline algorithm for large POM-DPs. So here is a comparison between policy tree. So on the left, you have policy tree. And here is a policy graph or finite state controller. So you see you have less nodes and you can have loops inside your policy. But how we do it? So first, our algorithm, POM-CGS, treat the POM-DP like a belief MDP. So we start from the initial belief states, and we also do Monte Carlo simulations. And for each encountered action observation history, we build a belief node. And at some point, we found, okay, at some point, I'm going to add a new node here. And I found, wait, before adding it, I found the belief here is quite similar to a existing node I have here. So I don't really need to add this node again. So I can directly merge the path to my existing node because their beliefs are quite similar. And how we do the merging? So before we do the merge, we first check the distance between those 2 beliefs. So we define a similarity matrix. We use the norm 1 distance. And if for example, if there's a new node and if there's a one node in your current FSC have the belief that has this property, then you can just merge the path. But why it works? Because in POM-DPs, the optimal value function is piecewise linear convex, so it's continuous in belief space. This means similar belief usually have similar optimal actions, and merging nodes with very small belief difference have very minimal impact on the final policy quality. So those properties makes POM-CGS works quite well on discrete settings. But for continuous settings, for example, for continuous states, we need the state discretizations, so you can then compare beliefs. And for continuous observations, in this paper we use clustering, so we use k-means to group similar observations together, so it treats like a discrete observation case. And for continuous actions, we use action progressive widening, so which is a quite standard online planning technique, but we apply it to the offline policy computation. And here's some performance. So POM-CGS performs quite well on standard POM-DP benchmarks. But in fact, not just about speed, but not just about performance, but also speed. POM-CGS is quite fast. For example, on the light-dark problem, POM-CGS just needs seconds to compute a complete policy. And to sum up, POM-CGS enables quite efficient offline planning in large POM-DPs, but still cannot compare with online planning methods, because online planning methods don't need to derive a complete policy. And POM-CGS combines Monte-Carlo sampling with belief node merging, so it reduces the search complexity. You don't need to have each history with a unique node. And it produces a compact FSC policy for direct execution, so you can validate a policy before you execute it. And this results to a practical and quite fast offline solution for POM-DPs. It bridges online techniques to offline POM-DP plannings. And especially, POM-CGS does not require explicit transition and opposition models. You just need to give a black box simulator to POM-CGS, and it is enough. And then I want to introduce our POM-CGS algorithms Julia package. So now the POM-CGS algorithm is an official Julia package, and it's really easy to use. So now I'm gonna take 1 or 2 minutes to show a demo. So I'm not sure if everyone is familiar with Julia. Oh, I will take it as a no. Okay. So I'm gonna first create a new environment, just in case you don't mess up. Just in case you don't mess up with your previous dependencies. POM-CGS. Oops. And then you can install POM-CGS. So like that, POM-C graph search. So this is like a pipe install in Python. I already have it in my laptop. Okay, once you have it, you can use it. So this is like Python imports. We also add some Python POM-DP packages. And we give a random seed to make sure everything is reproducible. Okay, so now let's define a POM-DP. So we define a rack sample problem. Rack sample POM-DP 7.8. And now we can define our solver, so POM-CGS, solver POM-CGS. We give a POM-DP. We define a belief merging threshold. We define some other parameters, for example, just for the demo. And this is gonna take some seconds. Just to give more information, so the rack sample problem is a classic POM-DP benchmark. And for rack sample 7.8, it has around 12,000 of states, 13 actions, I remember, and 3 stochastic observations. So Z is not that small, but also not a that big problem. And it's a very suitable case for testing. And usually for previous offline method like SucksOp, it may take like around 10 minutes to solve it, including the initialization time. So the initialization should finish in some seconds. Come on, come on. Come on, come on. Okay. Okay, now we finish the initialization, we can solve it. So solve POM-CGS, POM-DP. Okay, so POM-CGS maintains a lower bound and the upper bound. So the lower bound is the current policy's evaluation value, and the upper bound is computed using an MDP heuristic. And maybe just give information. So my laptop is a quite old one, so it has 1.4 gigahertz i5 CPU. So you should have at least 3 or 4 times faster than mine if you're using a normal i7 computer CPU. So yeah, so you see they are gradually converging. So it should finish in 10 seconds, I guess. Yeah, so finished. So you have compute a complete policy with around 600 of FSC nodes, and you reach to a value of 19.44. So yeah, so easy. Um, um, so oops. So so if you are interested, we have everything in details in our Julia package, in our GitHub package about how to use this server. We have very detailed instructions, and also we provide some guidance of common benchmarks, and you can tune it very easily. Yeah, so that's it. That's all my presentations.
We have time for a couple of questions. I'll just go to the hand I saw first.
Thank you. How do you compare it to optimal?
Since this is a sampling-based approach, our method cannot guarantee optimality, but comparing with optimal or epsilon optimal method like Saxop, I would say usually the performance is quite similar. Our algorithm can give near optimal performance, given enough sampling budget. For example, give enough particles, enough simulation budgets. Yeah.
Okay. Quick question. So with the merging of belief states, you do a similarity distance. To me, this seems a lot like optimal transport because you're comparing probability distributions. Did you consider any other similar, like graph similarity metrics or optimal transport measures from the literature? Would that prove more effective because you can decide better states, or was L1 enough?
So in the POMDP case, currently we at least I think the measure of belief is the most accurate one. Maybe you can use some heuristics to merge belief nodes, but since in POMDPs the value function is piecewise linear in the belief space, so I think merging beliefs is the most accurate measure. But maybe we can replace L1 distance to other things. For example, you can use other measures, especially for continuous state space. Yeah.
We have time for one more question. In the meantime, could I just ask the next speaker to set up? Yeah. But we have time for one more.
Okay.
Yeah.
So there is this classical policy iteration procedure which uses FSCs as the representation. I wonder if you've compared with that.
You mean Hansen's work?
Hansen, yes.
Yeah, Hansen's work is really, really a classic, but I don't think it's state of the art anymore. Yeah.
Okay.
All right. With that, let's thank the speaker again.
Thank you.